Hello, this is True Socrates, and today's video is about the concepts of linear independence and linear dependence. So in this video, we are going to learn the definition of these two concepts, linear independence versus linear dependence, and we will also see the minimizing theorem, which is the main tool that we use in order to decide whether a set of vectors is independent or dependent. So first, let's read the definition together. A set of vectors S consisting of v1, v2 to vn, these vectors are from Rm, is linearly dependent if we can find a non-trivial solution x made of the scalars x1 through xn from Rn, where at least one component, x sub I, is not zero. To the homogeneous system, x1 v1 plus x2 v2 all the way up to xn vn is the zero vector. We call this equation the dependence test equation for S. An equation of this form, where at least one coefficient is not zero, will be referred to as a dependence equation. However, if only the trivial solution, where x is the zero vector, exists for the dependence test equation, we say that S is linearly independent. We often drop the adjective linearly and simply say that a set of vectors S is dependent or independent. So I hope you remember that in section 1.6, we studied these homogeneous systems of equations. And now we see why they are important. So let's start off with the standard basis set of vectors, which comprise of E1, E2 through En, and they are from Rm. Now, these standard basis vectors, if you recall, E1 is the vector where the first component is 1 and everything else is 0. And similarly, E2 is 0 everywhere except for the second component. So what we're going to do is we're going to take the test equation. So it's supposed to be x1 v1 plus x2 v2 and so on. But here we have x1 e1 plus x2 e2 all the way up to xm em. Set that equal to the zero vector, and we're going to find all the solutions. However, these are very simple vectors. So if we make x1 e1, we will have x1 in the first component and 0 everywhere else. And similarly, if you make x2 e2, you're going to get 0 x2 and 0 everywhere else. So if we complete that linear combination on the left, we will simply get the vector x1, x2 through xm. And we saw this, of course, in section 1.1, when we said that every vector in Rm, in this case, can be expressed uniquely as a linear combination of E1 through En. So in other words, our test equation simplifies to x1 to xm on the left and the zero vector 0m on the right. So, of course, what are the solutions to this very simple equation? There's only one of them. x1 has to be 0, x2 has to be 0. All of these coefficients will have to be 0. All right, so our only solution is x1 is 0, x2 is 0, and so on. So we only have the trivial solution to our dependence test equation. And therefore, we can conclude that we have a linearly independent set. So the standard basis set of vectors is linearly independent. Now, of course, these are very, very simple vectors. So what do we do if we have more complicated vectors? Okay, so for this, we have to remember what we did in section 1.6. So we said, well, if you're solving a homogeneous system of equations, all you have to do is put the coefficients into a matrix and then find the rref of that matrix. If you have a free variable, then you have an infinite set of solutions to that homogeneous system. If you only have leading variables, you don't have free variables, then you have only the trivial solution to that system of equations. So we can formalize that idea in what we call the minimizing theorems. So suppose that S, V1 through Vn, is a non-empty set of vectors from Rm. We form the matrix A, which is called the matrix of S, where we put the vectors V1 through Vn into the columns of the matrix of S. And then we get the rref. So suppose that R is the rref of A. What did we say? If R only has leading variables, then we have only the trivial solution, so therefore S is already linearly independent. However, if R has at least one free variable, so there are non-trivial solutions, then S is dependent. But the minimizing theorem says something more. In this case, where we have a free variable, suppose that I1, I2 through Ik are the column numbers of the columns of R that contain the leading variables. And let's put together into a set S prime the vectors Vi1, Vi2 through Vik. In other words, these are the original vectors in S that correspond to the columns in the rref that contain the leading ones. This set of vectors S prime is a linearly independent set. So starting with a dependent set, we extract a subset of the set, which is linearly independent. And the span of this subset S prime is the same as the span of the original set, S. Furthermore, every vector in S minus S prime, in other words, the vectors of S corresponding to the free variables of R, can be expressed as a linear combination of the vectors in S prime, using the coefficients which are found in the corresponding columns of R. Okay, so that part is new. We're going to see that in our example. So just some notes about what we see in this theorem, because there's a lot going on. So S, the matrix of S, this symbol, remember this is where we assemble the vectors of S into the columns of S. So that's why the matrix of S is a good name for this symbol. S prime are the original vectors corresponding to the leading columns of the rref R of S, and S minus S prime are the vectors in S which are not in S prime. So they are the original vectors in S corresponding to the free variables of the rref. And the minimizing theorem says we can express the vectors of S minus S prime in terms of the vectors in S prime. And it doesn't take a lot of effort to do. All right, so let's take a look at this example. We have this set of 6 vectors from R5. Okay, so here they are. And we want to decide whether this set is linearly independent or dependent. So the minimizing theorem said, make the matrix of S. So this is our matrix for S. The columns are made of these 6 vectors. So there are 6 columns. Every vector is from R5. So there are 5 rows. Okay, so check it out. Who is in column 4? That should be our 4th vector in this set. So we have -5, 2, -2, 3, -2. Okay, as I always tell my students, the first rule of math, make sure you copy the problem correctly. Okay, so the minimizing theorem says, look at the rref of this matrix. So, compute matrices, rref, boom. Okay, so we have leading variables. They're in columns 1, 2, and 4, but we have free variables. They're in column column 3, column 5, and column 6. Okay, so let's write down what we said. Our leading variables are found in columns 1, 2, and 4. So therefore, S prime is made of the original vectors found in columns 1, 2, and 4. So that is V1, V2, and V4. So that is our S prime. So the span of these 3 vectors is the span of the original 6 vectors. So this is a very important concept, because why should you use 6 vectors to create a span if all you need is 3 vectors, right? It's more efficient to use only 3 vectors instead of 6 vectors. So the free variables are found in columns 3, 5, and 6. So our S minus S prime are V3, V5, and V6. All right, so now let's understand the minimizing theorem. It says that S prime, which is made of V1, V2, and V4, is already a linearly independent set of vectors. Okay, so why should we believe that? So we have to form the test equation where we want x1 times v1 plus x2 times v2 plus x4 times v4 is the zero vector. Okay, in this case, that would be the zero vector 0, 5. Okay, so we want to see if there are any non-trivial solutions to this test equation. Now, I've gone ahead and labeled the matrix of S and just called it A, and the rref, of course, we call that R. The key idea to proving independence is that the solutions to the original homogeneous system, AX is the zero vector, and the solutions to the reduced system, Rx is the zero vector, are exactly the same. So any solution for Ax is the zero vector should also make Rx equal to the zero vector, and vice versa. Any solution to Rx is the zero vector must be a solution to Ax is the zero vector. Okay, so let's think about this dependence test equation. We only want x1 v1 plus x2 v2 plus x4 v4 to add up to the zero vector. What happened to v3, v5, and v6? We had 6 vectors in the beginning. Well, you can think of them as being there, except they're invisible, so that means that they have been killed by a coefficient of 0. Okay? So in other words, when you multiply by x, think of multiplying by x, we are multiplying by a vector with zeros for x3, x5, and x6. So let's put in our matrix X. It's going to be 6 by 1 because we have 6 coefficients. So we only have x1 and x2 and x4. The other coefficients are 0. So let's put 0 here, and 0 here, and 0 here. Okay, but remember the meaning of matrix multiplication. We take column 1 multiplied by x1, column 2 multiplied by x2. But we have 0 here, so column 3 does not contribute, column 5 does not contribute, column 6 does not contribute. So we only get column 1 times x1 plus column 2 times x2, and finally column 4 times x4. Okay, but again, oh wait a minute, doesn't this look familiar? This looks like E1, E2, and E3. Okay, not E4, but E3. It is in the 4th column but it's actually E3. But if we add that all together, let me borrow one of these, we are going to get x1 in row 1, x2 in row 2, and x4 in row 3. Okay, but we want that to be equal to row, I'm sorry, that was undo. We want that equal to the 0 vector. So of course, we want x1 to be 0, x2 to be 0, and x4 to be 0. So the only solution to Rx is the 0 vector, where the coefficients of v3, v5, and v6 are 0, are x1 equals 0, x2 equals 0, and x4 equals 0. Okay, so therefore, our set v1, v2, v4, which we called S, let me just copy it up here. I'm sorry, S prime. Therefore, S prime, made of these 3 vectors, is linearly independent. Okay, so let's now focus on the last part of the minimizing theorem. It says that every vi, which is in S but not in S prime, and these are our vectors in S minus S prime, each of these vectors can be expressed as a linear combination of the vectors in S prime, which were v1, v2, and v4, using the coefficients found in the corresponding column of R. Okay, so what is that corresponding column? Let's take a look at v3. Okay, so v3 corresponds to a free variable. Okay, the entries there are 4 and -5. Okay, we're going to use exactly the same idea that we used earlier to show that S prime is linearly independent. We are going to multiply by coefficients, but instead of x1, x2, and x4, we want something that will obviously add up to the 0 vector and involve v3. Okay, we're going to ignore v5 and v6 for now. Let's focus on v3. So if I want v3, then I need a coefficient for v3. I'm going to put 1. Okay, we're going to see in a minute why I'm putting 1 there. I said we are ignoring v5 and v6, so that means we're going to put zeros in v5 and v6. Okay, we're not going to use them. So, how do I make the linear combination add up to all zeros? Okay, so I already have a 1 for x3, which means that I am multiplying column 3 by 1. Okay, so by putting a 1 here, I'm guaranteeing that v3 appears in the equation. Okay, so far I have 4 and -5. I want to get zeros though. So I need to get rid of that 4 and that -5. But wait, look at column 1. There is a 1 there where the 4 is found. So if I include column 1, I can get rid of that 4 by multiplying column 1 by -4. So I now have -4 plus 4. That's now 0. Okay, but I still have the -5. So guess what? I have column 2 here. So now I am going to add column 2 into the picture. and my picture just hid 0, 5, and we want to get rid of the negative 5, so we multiply this by 5. Let's see. Yeah, I can scoot myself over there. Okay, so does that really add up to 0, 5? Let's double check. Minus 4, 0 there for the 5, plus 4, aha, 0. Negative 4, who cares? That's a 0. Plus 5 minus 5, that's a 0. Everything else 0 here, everything 0 here, everything else 0 here. Okay, so those are the correct coefficients that we need to get the 0 vector if we force a 1 for x3. So I need a negative 4 here and a positive 5 here, and v4 does not play a role. That will also be a 0. All right, but we said that the key idea here is that the solutions to ax is the 0 vector and the solutions to rx is the 0 vector are exactly the same. So therefore, if you multiply A, the original matrix, by the same x, we should get the 0 vector also. This time, it's not obvious at all that we will get the 0 vector. So let's see. We want column 1 multiplied by negative 4. Make that a matrix. Column 1 by negative 4. Column 2 multiplied by 5. Column 2 multiplied by 5 plus column 3, which belong to a free variable. Okay, so that is our linear combination. There's an invisible 1 over here. Do we get the 0 vector? Click, boom. That is the 0 vector. What do we have on the left though? This says negative 4 times v1 plus 5 times v2 plus v3 is equal to the 0 vector. Okay, so what can we do now? We can solve for v3. We get v3 equals, move the minus 4v1 to the right, we get 4v1, move the plus 5v2 to the right, we get minus 5v2. But wait a minute, 4 and minus 5. Where did we see 4 and minus 5? Ooh, right here in the third column of our rref. Okay, so the minimizing theorem said every vector corresponding to a free variable can be expressed as linear combinations of the vectors in S prime, the vectors corresponding to the leading variables, using the coefficients found in the column for that vector. So let's finish this off. We have 2 more free variables. They are in column 5 and column 6, v5 and v6. Okay, so let's solve for v5. The coefficients that we find there are negative 4, negative 3, and negative 8. Who are the vectors corresponding to these 3 coefficients? Negative 4 corresponds to this leading 1. So that is in column 1, that's v1. Negative 4 times v, so 1. The minus 3 corresponds to this leading 1, that's in column 2. So that's minus 3 times v2. Put an arrow here. Be careful with the minus 8. The minus 8 corresponds to this leading 1, which is in column 4. So that is minus 8 times v4. Okay, always look who is the leading one corresponding to each of these coefficients. Okay, so for V6, we got 3 corresponding to column 1, 3V1, and we have 2 corresponding to column 2, so 2V2, and 6 again corresponding to V4, not V3, but V4, plus 6 times V4. Okay, so let's check that these coefficients are correct. So let's put minus 4 into x1, minus 3 into x2, and minus 8 into x4. Okay, we're not using V3 or V5 and V6. We are supposed to get V5. This is our V5. Okay, so let's check. Boom, there is our V5. Minus 3918 minus 1. Magic. No, it's not magic, it's math. All right, let's check the other one. We want 3V1, 2V2, no V3, 6V4, no V5, no V6. We're supposed to get V6. And we get, boom, that really is our V6. Okay, so that's our video for today. I hope you enjoyed it. To be honest with you, I think the minimizing theorem is one of the most amazing theorems in linear algebra. So, until the next time, this is Truth Socrates. You'll find me on Facebook. You'll find the 4th edition on Facebook. And of course at kendallhunt.com. Thank you for watching, and I'll see you next time. Enjoy the rest of your day.